Good evening, students. If you have any queries from your previous run of the interaction session or the course, you can please feel free to write it down here in the chat box. Otherwise, I can proceed with the current live interaction session. Okay, it seems that you guys have no queries. Okay, so no problem. Then we can start with our current live interaction session. Okay, so good evening, everyone. Welcome you all to this live interaction session of the NPTEL. The course is Sustainable Power Generation System, being taught by Professor Pankaj Kalita. And I am Rohit. I am a scholar at PhD scholar at IIT Bombay. I'll be taking this live interaction session. This is live session 9 being conducted 24th of September 2024. So generally this is about me. So you can follow this link to know more about me. The teaching methodology that we follow every Tuesday from 7 to 9 p.m. So we have a discussion on the topic that are being taught in the weekly lectures, and then we have some doubt clearing and interaction with the students. Also, if you have any queries, so feel free to ask your queries anytime during the live interaction session by raising your hand, or you can also post your queries into the chat box. So if you think your queries need good amount of involvement of other TAs also or professors, so you can raise it on the discussion forum also. That will benefit the all students who are registered in this course. So I hope you guys must have gone through the previous weekly lectures that talk about the ocean thermal energy conversion system. So this is kind of uh, sustainable energy system that we tap the thermal energy that is stored in the ocean. Okay, so whatever the temperature difference between the surface water and the deep water. So generally what happens, there is a Lambert's law. So we'll discuss about that Lambert's law in the upcoming slides. So what happens when the sun, actually the solar radiation hits the surface of the water, so the upper layer of water actually gets more heat, so it is heated to somewhat 25-27 degrees Celsius. But as you go down deep water, the temperature, the absorbance of solar radiation gets low, because most of the energy is actually absorbed by the upper layers, and the lower layers actually get very few amount of energy to get it absorbed. So there is a temperature difference. That temperature gradient or temperature difference, or you can say a thermal gradient, can be utilized to run basically organic Rankine cycle. So these organic Rankine cycle basically runs on refrigerant. So we use refrigerant instead of steam that we use in a common power plant. And using these, we can have a small type of power plant that can be actually utilized to provide power to a generator and then the electricity to the nearby areas. Okay, so basically ocean thermal conversion system. So the surface water which we consider here is up to the 6 meter in depth, and it is much warmer. Like if you can see the distribution of the surface throughout the graph here, you see that there is less than temperature of 18 degrees Celsius. You can see nearby the ocean continental shelf, and as you go towards the continent, you can see a more warmer temperature. So these temperatures can be utilized to generate ocean thermal energy conversion systems. and these are basically suitable for base load generation. So what is the base load? So base load are basically a bare minimum load that can be supplied through the any power generation system. So base load have so when you study a power generation system, so it can have a base load, it can have a varying load also. So generally when you have a power plant, so basically power plants are basically designed for a base load generation systems, and when but then you have some coal power plants, or they can vary their load according to the variation in the load from the electricity demand side. So there is always a tussle between the generation and demand side that actually decides how the power will be generated, the quantum of power will be generated, and how it will be transmitted and distributed. Okay. Now, if you see the OTEC basically ocean thermal conversion system. So OTEC types can be open thermal cycle power plant. Okay, closed cycle power plant. So open cycle power plants are basically also called Claude power plant. Closed cycle power plants are called Anderson power plant, and then we also have a hybrid cycle power plant. So if you see ocean thermal conversion systems, we have one warm here warm is written, but it is warm seawater from the surface. So warm seawater from the surface is actually taken, and then this is actually heat. You can see, yeah, evaporator. So here the refrigerant is there. So refrigerant, you can say ammonia is there as a refrigerant. Okay, so this is kind of organic Rankine cycle type of thing that you have studied in the previous slides also. The ammonia basically goes to the turbine, so it rotates the turbine, and then clubbed with generator that actually produces power. Then whatever heat is left out after the turbine is actually given into the condenser, and this condenser heat is actually then used to cool the flash chamber, and all those things are also there. So desalination water tank, everything is there. So they are basically a club type of systems. Okay, and to cool the heated refrigerant in the condenser, so where you can get the water, so water is actually taken from the colder depth of the ocean. Okay, from 1 kilometer below the surface, that has a very low temperature of 5 degrees Celsius. Okay, so that can be utilized to actually power the uh, take the heat away from the refrigerant in the condenser. Okay. Now products of the OTC plant. So OTC plants not only produces power, but it also produces desalinated water. So that can be used for irrigation and drinking purposes also. Okay, so we take the warm water from the surface air, then we run the OTC plant which generates electricity, and then similarly the water is also utilized to actually generate the desalinated water, and then cold water is discharged. Okay, so now if we see, I think there was a numerical here which is not saved actually. So yeah, this numerical. So we'll be having a lot of numericals in between, but the first thing which you can take is you can solve this numerical. So feel free to solve this numerical, and if you have any queries, please feel free to ask your question in between, so that you guys can have a good idea about how these things are actually varying. Okay, so try to solve this question. All the data are given. So calculate the required flow for a 8 megawatt. So you have got the power output 8 megawatt, and then considering the ocean surface is 25 degrees Celsius and deep sea water is 5 degrees Celsius. So you can get the delta, the thermal gradient you can get. Then take the specific heat of water and density of water is given. So it's just a formula based question. You just have to apply the formula and then generate the required answer. of the required flow rate. Okay, so I will wait for 5 or 10 minutes for you guys to solve this question, and if there are any queries in between, please feel free to ask. Okay, so now if you take the solve this question, so all the data are given, like P node is given 8 megawatt. So you need to convert it to watt. Okay, so now you know the P equal to Q rho Cp del T square upon Th. So you have to actually determine this flow rate. Okay, calculate the required flow rate for a 8 megawatt OTEC plant, and now you can see from this formula that power produced is directly proportional to the temperature difference, the thermal gradient, square of the thermal gradient. So now if you have got all the formulas, you know Th value of Th is 25. Okay, and all the values should be in Kelvin. Okay, so 25 is 298 Kelvin. Similarly, del T is 25 minus 5 equal to 20. Okay, रिमोट है क्या? बाप रे, अंदर वो कश्मीर बना दिया भाई. क्या बारिश हो रहा है? Okay, did you got the solution? Okay, no problem. Let me solve this question for you. So, okay, where is this? So 8,000 what into TH is 298, Q equal to rho is 1000, CP is 4200. So this has to be in joule. Okay, that is 5 uh, 20, sorry, 20 square. Okay, so now you can get the react flow rate data. Calculate how much is the value. Okay, so this is megawatt. Okay, and this is joule. So yeah, this is 10 to the 3 also watt. So 8,000 into 10 to the 3 is what? 298. So flow rate will come something around 1.7 meter cube per second. Okay, so this is the correct answer. Now, this is the another question. Try to solve it, guys, because this closed cycle OTIC system uses ammonia. This is a big question, so you have to put your concepts to testing actually in solving this question. So I am sure you guys will be able to do this. Try to solve it. Okay. So there is no problem in uh, because all the values are given here, and the isentropic efficiencies of turbine and pump are also given. Okay, so this has to be taken into account. So find the efficiency of OTEC plant. So OTEC plant uses ammonia. So okay, and working fluid installed near the coast of Tamil Nadu. So warm water at temperature TH 29 and cold water has a depth of 600 meter. TH is 8 degrees Celsius. Consider an allowance of about 5 degrees Celsius for the temperature difference required in the evaporator condenser for transferring heat, and assume that working fluid ammonia is evaporating at 24 degrees Celsius and condensing at. So whatever the properties of ammonia at 24 degrees Celsius and 13 degrees Celsius is required is given here. Okay. Isentropic efficiency are also given. So first thing we have to do is to draw a Rankine cycle, and then draw the this thing. Okay. Then you will be able to solve this question very easily. This will be something like this. Okay. And this is the actual isentropic, but this will flow like this. Okay, and similarly this is the required for pumping, but this will be something go like this. Okay, so you have to take into account all this because isentropic efficiencies are given. Okay, now try to solve this question because this is quite a understanding question, because when you try to solve this question you guys will have a good understanding about how the things are actually going into. How do you calculate the efficiency of a OTEC plant? And then the last question, we'll solve it if we get time. Otherwise, I will tell you guys to do it as a homework. Okay, so did you solve this question? This is what happens sometimes. Okay, so did you guys solve this question? Okay, let me solve this for you then. It seems like you guys have some issues solving this question. Okay, so no problem. I can solve this question for you guys. Okay, so okay. So first thing we have to do is to draw a Rankine cycle. Okay, so that we can understand what's happening inside. So let's take a blank slide here. Now you have a blank slide. Now draw the TS diagram. Okay. So this will this is a constant boiler heat addition, and then this should be the actual isentropic efficiency. But due to isentropic efficiency, this will be the actual path. And this should be actually followed, but due to isentropic efficiency, more work will be required in the pump. So now let's say this is 2, this is 2s, okay, this is 3, this is 4. Okay, so these are actually state which I am talking about, and this is 1. So it starts from here. So firstly the water is pumped, or you can say refrigerant is pumped, then it goes to heat addition, constant pressure heat addition, and then there is expansion in the turbine, and then it's condensation where heat is rejected, and then other processes are there. Now you know H1, so you have to follow the refrigerants which are enthalpy as given. So enthalpy of saturated liquid, that is ammonia at 13 degrees Celsius. Okay, so H1 you know, 241.5 kilojoule per kg. Okay, so I am not writing the units, you just take the common units. Okay, 2 kilojoule per kg. Now process 1 to 2 is basically isentropic compression. Okay, compression of liquid. But since there is isentropic efficiency also, so we'll take this into account. So pump work, basically pump work WP will be something like V into P2 minus P1. Okay, so that is 1.612 into 10 to power minus 3 the W2 V, and that is following. And then pressure, you know, pressure is given in the question, 9.725 in minus 6.813. So pressure is given in some other units, you have to convert it into the units required. Okay, so pressure is given in bar, so you have to convert it into kilopascal. So 1 bar equal to 10 to power 5 Newton per meter square. Okay, so based on that you have to calculate. Okay, and this is 24. so you guys can actually understand. Now you know the pump work something around 0.46 or 47. Okay, now you know the isentropic compression efficiency. Okay, so point 0.8 is the isentropic compression efficiency, so that is H2 minus H1 upon H2S minus H1. Okay, so you know the H2S minus H1 will be this divided by 0.8, and this value you know 0.469, so this will come out to be around 0.59 or something. Okay, this is 0.47, this is 0.59. Actual pump work will be there. Similarly, you can calculate the H2S because H1 is known, H1 is 241.5, so H2S value you can calculate 242.08. Okay, now similarly entropy at these states can be calculated because entropy is given in the previous here entropy is given, so based on that you can calculate the entropy. So entropy is similarly S3 equal to S4. Okay, S3 equal to S4. Now entropy you know, so entropy at S4 will be S1 plus X4 into SV minus SL, because here it is in vapor form and here it is in liquid form. Okay, so you can calculate it actually S3 equal to S4, and then you can calculate the entropy values here, so that you can calculate it by yourself. Then you get the values of vapor fraction, that is X4, that comes out to be something around 0.97 or something. So based on that vapor fraction you can actually calculate the enthalpy at 0.4. Basically that is why we wanted. So in turbine there is isentropic expansion, so based on that concept you actually apply, and then H4 equal to HS1 plus X4 upon HSV minus HSL, and that HSV and HSL are given, so H4 is something around 1419.8 kilojoule per kg. Okay, now all the values are known, but this value is actually 90%, so it will this will not produce this much amount, so it will produce less than this, so you have to multiply it by zero point 0.9 and then put the value, then work turbine will be obtained. Okay, so work turbine will be something around H3 minus, basically H3 minus H4S will be actual work turbine, and H2S minus H1 that has to be subtracted to the net work. Okay, so net work will be something around 39.7. Okay, and then you know the heat input H3 minus H2S. The H2S you have got it from here, H3 you know. Okay, so you can get the heat input, so efficiency equal to work output, that is net work WT upon heat input, so that comes out to be around 3.25%. Okay, so this is the correct answer for the efficiency here, 3.25%. So see the efficiency values are so low, actually very low. So this is why the ocean thermal power plant has, but then you are getting renewable energy here. You don't have to waste any coal, sorry, not waste, you don't have to burn any coal to get this energy. Even if efficiency is low, but there is some power generation that can be actually utilized. But one thing always remains, the cost of building this system. So if the cost is low and then even if efficiency is low, these can be actually rated. So now go through this question, and if you see if there is anything which you need to discuss, because I think the point is clear here. You have to actually apply the concepts which you have learned similarly, so to basically understand the output, work output. Okay, you can have a look at So you can have a look actually. Okay, so do you have any questions, guys? No questions? So I think then we can move to other. Also, I think we can move to the blank slides. Okay, so okay, so these are two typical questions that are actually very much important when you are going to solve the questions on number. So even if you have not got any good understanding about the numericals, but I will suggest you guys to actually practice these questions. So these two are very basic type of questions and that can clear your concepts very much. So these type of questions you can also expect in the exams also. Okay. So now I think we can move forward to classification and other things. Okay, let me share my whole screen then. Okay, so classification of ocean thermal energy conversion systems. So earlier I was saying open or cloud OTEC based system, then closed or undersea, then hybrid system. So this is floating OTEC power plant. So all the things are located here, just two pipes, one for hot water, then another is for cold water. Similarly, land based or shore based plant are also there, and self based plants are there. Okay, self is not so far away from the ocean, just like you see uh, oil drilling sites, so similar like this. Okay, I will not solve this question because I think you guys should try it yourself. Otherwise, same, it's the same, like you just have to apply that formula. Okay, and you will get the answer. Closed cycle OTEX. So this is kind of a closed cycle. So you get a water pump, evaporator. Okay, so everything is closed in a loop. So when you say closed cycle, so everything is in a loop. Refrigerant is in a loop. Okay, and then you take the warm water for evaporator and cold water for condenser. Okay, so warm seawater vaporizes a working fluid such as ammonia flowing through a heat exchanger, that is evaporator. The vapor expands at moderate pressures and turns a turbine blade coupled to a generator that produces electricity. The vapor is then condensed in heat exchanger here using the cold seawater pumped from the ocean depth through a cold water pipe. Okay, so ocean depth can be 1 kilometer. So condensed working fluid is pumped back to the evaporator to repeat the cycle. Then we have hybrid OTEC cycle. Okay, so something closed, some open type thing. So this is kind of closed, then this is open. Okay, so hybrid cycle combines the feature of both closed and open cycle system. The warm water enters a vacuum chamber which is flash evaporated. Okay, here after evaporator, it enters a flash evaporation chamber, which is similar to open cycle evaporation process. Okay, the steam vaporizes the working fluid of the closed loops on the other side of the ammonia vaporizer. The vaporized fluid then drives a turbine that produces electricity. Okay, the steam condenser within the heat exchanger provides desalinated water. This is kind of OTEC system which has been imagined for India. So OTEC plants in Kavarati and Navanikobar were initiated in 1980. A preliminary design of 1 megawatt closed Rankine cycle floating was prepared by IIT Madras in 1984. Okay. So in 1997, National Institute of Ocean Technology signed a memorandum with Saga University, Japan for joint development of 1 megawatt plant. NIOT plans to build 10 to 25 megawatts shore-based plant in due course by scaling up to 1 megawatt testing plant, then possibly a 100 megawatt commercial plant. So this is how it will work. Similar concept, everything, hot water, then cold water. Okay. Now we are moving to the quiz questions. So before we move to the quiz questions, I want you guys to, if you have any questions or anything which you want to discuss from uh, uh, the course or any lecture slides which you want to uh, point your questions. So please feel free to ask. You can also write it here in the chat box, or you can ask directly. Otherwise, I will suggest you can try this question, the example 9.3. So that is actually a good question. I think you can guys can actually try it out before proceeding for the quiz questions. Okay. Okay, so did you solve this question? I hope you guys are getting it easy to solve the questions. And if there are any problem, please feel free to ask. So there won't be any issue in actually understanding the concept. The underlying concepts are very much important when you are trying to solve some questions. Okay. So I think then we can move to the quiz questions now. Okay. So if you have any question in between, please feel free to ask. Okay, so this is this, I think this was done actually. So OTEC, Ocean Thermal Energy Conversion Plant in India is independent of. So weather variations are not so many dependent uh, on OTEC variation because the temperature difference is what we are more looking into. And since sea water is basically absorbs the solar radiation, like absorbs the energy from solar radiation that can actually be there itself. So independent of weather variation, temperature at depth of 7 kilometers from the ocean surface. This is also not done because 1 kilometer at the depth of ocean surface is that is the temperature that we are more care of. Wind induced wave is also doesn't have any effect because the temperature of the layer itself is considered. So independent of all of the above. Okay, so the correct answer is answer D. Okay, so see if you have got any questions. Okay, so going to the next question. Which of the following power generation system provides steady power output without fluctuations? So this is what we learned here, because most of the parameters are actually independent. OTC plant is independent, so it even if there are fluctuations, so it will provide steady power output. The minimum temperature difference required between ocean surface and the deep water. So this is what was 25 and 5 was. So minimum should be at least 20. Okay. Which of the following cycles is used for OTEC? So basically, Rankine cycle is used. This one, TS diagram, TS. So we solve the numerical also. So I think you guys should have an idea now about this cycle. Okay, this is how it looks like. Remove this. This is not here. Okay. So did you find any conceptual similarity between Rankine cycle and other Stirling, Brayton, Otto cycle? So all these cycles are actually different in nature, how they operate, what are the different conditions under which they operate. Okay, so you just have to understand about how why they are being used in. So basically in Rankine cycle they are generally used in steam power plants. Brayton cycle generally used in jet gas engines. Okay, Stirling cycle and Otto cycle are there. Otto cycle is basically this gasoline engine cycle. Okay, so this is what ideal Rankine cycle looks like. I put a diagram also here, so you guys can actually view this diagram and identify the different components on the TS diagram. So this is TS diagram. So you can actually identify. So this is kind of a TS diagram. So the superheating is here. This is not there in case of OTC. Superheating not there. Direct can get it from here. So this is actually boiler. Okay, this is boiler. Then this is turbine, and then this is condenser, and this is pump. Okay, this is how it works. Okay, so did you have any questions regarding this? Okay, no questions. So I think we can go ahead because more than 5 or 6 questions are left now. So which region is referred to as best location for setting up OTEC plant? So tropical regions are the best because they get the maximum sunlight, solar radiation. Which type of OTEC plant is built on the top of continental shelf? So this was floating type, then land based, shelf based. So continental shelf has shelf based OTEC plants. And which of the following is used as a working fluid in closed cycle? So working fluid is always refrigerants, ammonia or something. Which characteristic required in the working fluid of closed cycle OTEC system? So it should have a low viscosity. Okay, and a low boiling point also. To generate low pressure steam, warm water is pumped through. So it is pumped through what? A heat exchanger. Okay, low pressure steam. So evaporator is generally a heat exchanger. Calculate the efficiency of OTEC plant if temperature of warm water in ocean surface 26 and temperature of cold water is 7 degrees Celsius. Now you have to calculate the Carnot efficiency. So you know the formula for Carnot efficiency 1 minus T1 upon T2. Okay. So T1 is the temperature of source to sink and T1 is the T2 is the temperature of source. 1 upon T2 upon T1 I should say. Okay. Now calculate and check whether you get the correct answer. Okay, so did you got the answer? No? So it's just a easy question. So you just have to 1 minus, and everything has to be in Kelvin. Okay, so 273 plus 7 equal to 280, and then divide it by 273 plus 26 is something 299. So that comes out to be 6.37 or something. Okay, so correct answer is answer B. Now question 11. Find the quantity of water to be pumped on the ocean surface with cold water at this and 1 megawatt assume the density. So similarly you have to apply this formula P equal to Q rho Cp del T square upon Th. Okay. Now P, you know this 1 megawatt. Q you have to calculate. You need to find the quantity of water to be pumped, and then rho is water 1000 kg per meter cube. Cp value you know, and del T you also know, 27 and 8 degrees Celsius at depth. So 27 minus 8 equal to 19, and Th you know 27. So put everything. So units should be temperature units should be in Kelvin. So you can actually easily, and temperature density of ocean water is given at 1010 kg per meter cube. Okay, so don't take 1000. So try and calculate this question. And I think this is the second last question, and then you we can complete this session. Okay. Okay, so did you got the answer? No? So put the values. So uh, the value here is 1. Sorry, 1000 into 10 power 3. Since it is megawatt, so into 300 upon 1010 into 4200 into 19 square. So correct answer will be 705.6 meter cube per hour. Okay. Determine the overall efficiency of the OTEC plant with warm water this and the temperature cold water is this. Relative efficiency factor assumed as 0.49. So you have to calculate the efficiency of the system. Okay. Okay. So I think let me solve this question for you guys. So this is simply a Carnot cycle efficiency, and you need to since overall efficiency and the relative efficiency factor is given. So multiply the Carnot cycle efficiency with this 1 minus, sorry, 1 minus. So 4 degrees Celsius is 277, and then warm surface is 302 Kelvin. Okay, so this comes out to be around 0.0406 in 200%. So correct answer is 4.057. So thank you for attending this live session. So this was interesting about ocean, interesting to know about the ocean thermal energy systems. If you have any question, please write it to me on this email ID. Otherwise, you can always put your questions in the chat box, discussion forum, or anywhere. So we'll meet again on the next Tuesday. Okay, so go through the live lectures, weekly lectures, and that will help you guys to solve the assignment questions also. So thank you once again.